LeChatelier's principle is extremely important when it comes to chemistry, especially questions that deal with equilibrium. But what is LeChatelier's principle? LeChatelier's principle can be sort of broken down into a couple of main steps. First, we have some system that's already at equilibrium. So we have a system that is at equilibrium. What happens to that system then is some sort of change. And we can see this change in a multitude of ways that we'll get into later into the video. These changes can include changes in volume, pressure, heat, or even concentration of different products. But here's where LeChatelier's principle sort of really comes into play. After the change, LeChatelier's principle tells us how the system restores back to equilibrium. How does it get back to its sort of original state? We can see LeChatelier's principle in action in a couple of main examples. And for these examples, we'll use some random chemical equation like X gas plus Y some gas goes to Z, which is some solid. And we can use this base equation to understand different types of principles that fall underneath the idea of LeChatelier's principle. The first thing that we can look at is how different concentrations of different reactants and products can have an impact, and how LeChatelier's principle tells us how to restore back to equilibrium when one of these changes. In this example, let's say that we add an excess of this Z solid. So the change is that we have added excess Z solid. Given that our system is already at equilibrium, our Q value is already equivalent to our K value, or our K concentration value. But by adding excess Z solid or a product, obviously that isn't the case anymore. And now Q is not equal to our K. But how does the system restore back to equilibrium? For that, LeChatelier's principle tells us that the systems that are originally in equilibrium, when are changed, try and revert that change as much as possible. Essentially, in this situation, if we add an excess amount of Z solid, the reaction will proceed in the reverse direction. So the reaction will proceed in the reverse direction. This means that more X gas and Y gas are created and Z solid is lost. Because when you've added excess Z solid, this obviously unbalances the equilibrium. And because of that, the system tries to revert itself to ensure that X, Y, and Z are all in their own concentrations that relate to each other as per the K concentration. Another example of this we can see in our K when it relates to gases. Using our base equation once again of X gas plus Y gas goes to Z solid, we can take a look at the system in a closed container, for example. So in our second example, we have some closed container. And all of a sudden, the volume of this container triples. So we'll have this volume set as V and this volume set as 3V. Image is not the scale, of course. But what happens again to the system when we've made such a big change? Well, according to the ideal gas law, if we increase the volume of a system, keeping all things else the same, the pressure of the system will decrease. So as our volume increases, our pressure decreases, which means that our K constant for pressure is now not equal to K. Because our pressure has decreased, the pressure within the system is no longer at equilibrium. So how does the system respond? Once again, we have to look at our base equation. And in this equation, we had two gaseous products on the reactant side and one solid product on the product side. Because of the fact that our pressure of the system has gone down, the equation itself must again proceed in the reverse direction in order to revert sort of the changes that have happened to come back to equilibrium. Because of how the system is in fact built, where two gases create one solid, we need to increase the amount of moles of gas in order to increase the amount of pressure within the system, because the moles of gas and the pressure within the system are directly related. So once again, the system goes in the reverse direction, because when we increase the volume, we need to increase pressure as well to go back to our original sort of system, and to do that, we have to increase the amount of gaseous products or gaseous molecules within our system itself, meaning that we need to proceed in the reverse direction to increase the number of moles of gaseous molecules or elements. The third, and one of the most unintuitive but can be very easy ways that we can also look at LeChatelier's principle is when it comes to thermochemistry. Once again, we'll rewrite the chemical equation as stated above as some X gas plus Y gas goes to some Z solid. But this equation has a delta H of negative 56 kilojoules, which means that we have an exothermic reaction. The reaction releases heat. What happens, for example, if we decrease the heat artificially or increase the heat? Well, to look at that, we can sort of think of heat as a product or a reactant within a system. And we can rewrite this equation from X plus Y to Z as X gas plus Y gas goes to Z solid plus heat. The reason why you put heat in the product side is because we have an exothermic reaction as given by a negative delta H. In this situation, what happens if we remove heat artificially from the system? We can treat heat as a product in this case, and if we remove heat from the system, once again, we will go in the forward direction. Same thing as what we did with different concentrations and removing concentrations of different products and reactants. If we remove heat from the system, to ensure we go back to a state of equilibrium, we will once again try and move forward in order to produce more heat to ensure that we are at our equilibrium sets of heat at our equilibrium system. Overall, LeChatelier's principle can prove very effective when it comes to things such as changing concentrations, looking at different pressure values, and even when it comes to different types of thermochemistry. Overall, it's a very useful tool for most equilibrium questions and can be very important, and as well as a decisive step that helps with your chemical intuition.